Welcome to measurements and their errors. In physics, accurate measurements are essential because experiments are used to test theories and calculate values. However, every measurement has some level of uncertainty. In this topic, we will explore units, accuracy, precision, uncertainties, and how errors affect results. Role of measurement in experimental physics: SI base units in the A-level specification, SI prefixes and powers of 10, derived units and unit consistency. Measurement underpins all experimental physics. Physical laws, equations, and models are only meaningful when they are supported by reliable and valid measurements. In practice, every quantity measured in physics, such as length, time, mass, or electric current, is subject to limitations arising from the measuring instrument and the method used. For example, when measuring the period of a pendulum using a stopwatch, human reaction time introduces uncertainty that affects the final value. The A-level physics specification requires students to use the International System of Units, SI units, consistently and correctly. There are 7 SI base units, but A-level focuses on 6 of them: meter, m, for length, kilogram, kilogram, for mass, second, s, for time, ampere, a, for electric current, Kelvin, K, for temperature, and mole, mole, for amount of substance. The candela, which measures luminous intensity, is excluded from assessment. SI prefixes are used to represent very large or very small quantities efficiently and are an essential part of the A-level measurements and errors topic. Common prefixes include tera, T, 10 to the power of 1 squared, giga, G, 10, mega, M, 10, kilo, K, 10 cubed, milli, M, 10 cubed, micro, mu, 10, nano, N, 10, pico, P, 10 to the power of 1 squared, and femto, F, 10 to the power of 1. Students must be able to convert between prefixed units and express values in standard form. For example, converting 3.2 milliseconds into seconds requires recognizing that milli means 10 cubed, giving 3.2 times 10 cubed s. Derived units are formed by combining SI base units according to physical equations, and their correct use is required by the A-level specification. For example, force is defined by F equals ma, giving the derived unit kilogram ms squared, known as the Newton, N. Energy, measured in joules, J, has units kilogram square meter s squared, while power in watts, W, is kilogram square meter s cubed. Understanding how these units arise helps students interpret equations rather than memorize them blindly. Accuracy, precision, resolution and repeatability, random errors, causes and reduction, systematic errors, and zero errors, improving experimental measurements. Accuracy describes how close a measured value is to the true or accepted value, while precision refers to how close repeated measurements are to each other. A set of results can be precise but inaccurate if they are consistently offset from the true value, often due to systematic error. Resolution is the smallest change in a quantity that an instrument can detect, such as 0.01 mm for a micrometer or 1 mm for a ruler. Instruments with higher resolution allow finer distinctions but do not automatically guarantee accuracy. Repeatability refers to the consistency of results when the same person repeats an experiment using the same method and equipment. Reproducibility, which is closely related, considers whether similar results are obtained by different people or methods. Random errors arise from unpredictable variations in measurement conditions and affect the precision of results. Examples include fluctuations in electronic signals, variations in human reaction time when using a stopwatch, or slight changes in environmental conditions such as temperature. Random errors cause readings to scatter around a mean value rather than shifting them consistently in one direction. Random errors cannot be completely eliminated, but their effects can be reduced. Taking multiple measurements and calculating a mean is one of the most effective strategies, as positive and negative deviations tend to cancel out. Identifying and excluding anomalous results, when justified, also improves data quality. Using automated data logging equipment can reduce human-related random errors by increasing consistency and resolution. For example, light gates provide more precise timing than manual stopwatch measurements. Systematic errors affect the accuracy of measurements by shifting all results in the same direction, either too high or too low. Unlike random errors, they do not cause scatter but instead introduce a consistent bias. Common examples include zero errors, where an instrument does not read zero when it should, and calibration errors, where the scale of an instrument is incorrect. For instance, a balance that reads 0.05 kilograms when empty will add this error to every mass measurement. Parallax error, caused by reading a scale from an angle is another systematic error that can be reduced by reading scales at eye level. Improving experimental measurements is a recurring theme in A-level physics, particularly in required practicals and exam questions that ask for method evaluation. Improvements can target both random and systematic errors. Increasing the number of repeats and calculating a mean improves precision by reducing the influence of random fluctuations. Using instruments with higher resolution, such as micrometers or digital sensors, allows smaller uncertainties to be recorded. Systematic errors can be addressed through calibration, zeroing instruments before use, and using control measurements. For example, measuring background radiation and subtracting it from subsequent readings improves accuracy. Absolute, fractional, and percentage uncertainty, combining uncertainties in calculations, error bars, and graphical representation, uncertainty in gradient and intercept. Uncertainty quantifies the range within which the true value of a measurement is likely to lie. Absolute uncertainty is expressed in the same units as the measurement, such as plus or minus 0.1 centimeters. Fractional uncertainty is the ratio of the absolute uncertainty to the measured value, while percentage uncertainty is the fractional uncertainty multiplied by 100. For example, a length of 20.0 plus or minus 0.2 centimeters has a fractional uncertainty of 0.01 and a percentage uncertainty of 1%. When quantities are added or subtracted, absolute uncertainties are added. For example, if two lengths with uncertainties are summed, the total uncertainty is the sum of their absolute uncertainties. When quantities are multiplied or divided, percentage or fractional uncertainties are added instead. For powers, the percentage uncertainty is multiplied by the power. These rules allow students to estimate the uncertainty in a final calculated value, such as density or resistivity. Graphs are a powerful way to present experimental data. Error bars show the range of uncertainty in a measured value, usually plotted as vertical bars for y-axis uncertainty and horizontal bars for x-axis uncertainty. They help indicate the reliability of individual data points and whether a proposed relationship is supported by the data. For example, if error bars overlap significantly, it may be difficult to distinguish between competing models. In practical work, students should include error bars when uncertainties are significant relative to the spread of data. A-level expects students to determine uncertainties in the gradient and intercept of a straight-line graph using the worst-fit line method. This involves drawing the steepest and shallowest lines that still pass within the error bars of the data points. The difference between these gradients gives an estimate of the uncertainty in the gradient. The same approach can be applied to the intercept. This method reflects the impact of measurement uncertainty on derived quantities and reinforces the link between graphical analysis and experimental reliability. Orders of magnitude estimation, using estimation to check calculations, common exam mistakes and how to avoid them, summary and key takeaways. Estimation of physical quantities to the nearest order of magnitude is a specific requirement. This skill involves rounding values to the nearest power of 10 and using approximations to make quick, reasonable judgments. For example, estimating the mass of a car as 10 cubed kilogram or the diameter of an atom as 10 to the power of 1 m. Estimation is particularly useful when exact values are unknown or unnecessary, such as in femistyle problems. Estimation is a valuable tool for checking the plausibility of calculated answers. By approximating values before or after a calculation, students can quickly identify errors in arithmetic, unit conversion, or equation use. For example, estimating energy values using rounded figures can reveal mistakes of several orders of magnitude caused by incorrect prefixes. Common mistakes in the measurements and errors topic include incorrect unit conversions, misuse of prefixes, confusion between random and systematic errors, and incorrect combination of uncertainties. Students often lose marks by quoting answers to too many significant figures or omitting units entirely. In this topic, we have learned that measurements always contain uncertainty. Understanding errors, improving methods, and analyzing results carefully are essential skills in physics. Accurate measurements allow scientists to produce reliable conclusions. Thank you for watching.